Okay, so this is where I need to get to. So just to kind of recap, I guess it's probably a good thing to recap anyway. We talked about galvanic cells, and remember this is going to go back to our oxidation and reduction information. So oxidation is the loss of electrons, reduction is the gain of electrons. We did these back last year. We have an anode and a cathode that we work with in terms of these galvanic cells. Sometimes we have inert electrodes. For example, if we're going to move like iron 3 to iron 2, you would have to use one of these inert cathodes. Or hey,
is Eric here?
Well, he's here. He didn't do much, but he's here.
Oh, yippee.
Well, he was supposed to watch a video on Friday.
Oh, I gotta watch a video.
Or Saturday, or Sunday.
That's 3 days.
It was a 38-minute video. I know it was long, but. All right, so sometimes we have to use the inert cathodes because, pay attention to me, not him. Put that away. Don't me. You're on my list.
Good.
Okay, so then we would have to use some inert electrode for this. We have to use a salt bridge to balance charge, and we'll talk about that today in terms of what that means. And then you've got to have wire to be able to have your electron flow through a wire. And then they have this standard cell notation. You might end up taking this if you are in college. They might want you to do this. You don't have to do it for the AP exam. And then a lot of times they'll have a voltmeter that will measure this electrical potential. We talked about how to balance these. Remember, when you're doing this, you need to look at your electrons and see how many electrons are moving. Here's my pen. You have to figure out which one of these is, and we're not doing this in terms of, oh, shoot, I can't write on this thing. I don't understand why it won't let me write on here anymore. If it'll let me write on here. Oh, it does. Okay, then I don't have to take it over to Word. I'll just do it right on here. All right, so we're going to balance this redox reaction. If we look at this, we need to figure out which is being reduced and which is being oxidized. Remember, oxygen's a -2, so this side's a -8. Overall charge on this ion is a -1, so what does manganese need to be? +7. Okay, over here it's a +2. So we went from a +7 to a +2. Did it gain electrons or lose electrons? Charge went down. So what charges gained electrons, which means that this is reduced.
So how do we find electrons? How do we find what the charge is?
This?
Yeah.
This is a -2. The overall charge for this ion here is negative. See where there's negative signs here? So it's a -1 overall. So if this is a -1 overall, this is a -8. So what would give us a -1? That would be a +7. Our iron went from a +2 to a +3, so it lost electrons. So it was oxidized. Okay, the charge went up, so it was oxidized. So our reduction here was our manganese. So manganese, MnO4 minus, plus 5 electrons, yields Mn2 plus. Sorry, Austin, this is going to be a lot of review from last week.
That's fine. That'll be good.
And then our iron down here, Fe2 plus, would yield Fe3 plus an electron. Well, we've got to get this to balance out, so we're going to have to multiply this by 5. Does that make sense? So if I multiply that by 5, and I do that throughout, this is a 5 and this is a 5. So our overall reaction, our electrons are going to cancel. This is going to become MnO4 minus plus 5 Fe2 plus yields 5 Fe3 plus Mn2 plus. And what you need to note here especially is N equals 5 electrons. Keep this in mind. That's going to come into play later on. Probably not today, unfortunately. I had hoped for that, but it's not going to happen. Sorry, getting sassy. You good? You ready to move? All right. So when we go through this, we talked about these different parts of this, the different volts, the different voltmeters. We talked about things called standard conditions. These are important to note. That's not going to become important today, but it will at some point. Standard conditions, 1 atm for gases, 1 molar for your solutions in here, and then 25 degrees Celsius or 296 K. We call those not conditions or standard conditions, and they're denoted with a not sign on these values. So the E cell not, or the EMF not, or the E cell not is going to be the same thing, and those are all going to be at standard conditions. And if you think back to our entropy and enthalpy values, those are all at not conditions. The delta G, the delta S, the delta, remember? If you look in that table that I had you look at. Okay, so we'll talk about how these are working. We have these standard reduction potential tables that we worked with. We talked about these acronyms and OX, that's where your oxidation is going to happen. And then we talked about red cat. So red is going to, reduction is at your cathode, which means that your anode is going to be your oxidation. So an ox and a red cat. An ox. The other way that people sometimes remember this are these are both vowels and these are both consonants. And if you think about your car battery, you know how your car battery has a red and a black? Okay. The red section of your car battery, that's your cathode for your car battery. That's why it's red, because that's where the reduction is happening. And then your anode is going to be your black lead. And that's why you can't reverse those things, because bad things happen because you're switching that battery around and bad things happen. Okay. So this is where we left off at. New. All right. So this is zinc and this is copper. Okay. This is our cathode and our anode, but we could potentially figure that out. I don't think it'll let me. No, I guess it won't. We could figure that out just from data. Okay. So if we go back and we look at those reduction potentials and the over here, you should be able to find the reduction potentials in your chart for zinc and for copper. So copper, you should see one on there. I found copper first, so I'm going to use that one first. So Cu, and it goes from 2 plus 2 electrons, and that goes to copper. And the value for that is 0.34. Okay. And then if you keep going down a little bit, you'll see zinc 2 plus 2 electrons is zinc, and that's going to be a negative 0.76. Okay, so I got those from this chart. My copper is right here, and you need to pay attention because it said in that it was losing 2 electrons. It showed us on the diagram that it was, because there's cases where it's losing 1 or this is losing 1 and those values are different. Here we're losing 2 electrons, so it's 0.76. Now I can look at these values and I can see which one is my anode and which one is my cathode. Okay, this one is a more positive value compared to this one. This is my cathode. This is going to be my anode. If I want to figure out the voltage in this, I do cathode minus anode. So my cathode is this, it's 0.34. I'm going to minus a negative 0.76, and that'll give me my value. 4 minus negative 0.76, and I get 1.1 volts. Okay, so cathode minus anode. She shows you how to do it slightly differently in hers. If you want to go through and look at the math that she's shown you, she actually flips one of these equations around, then she has to flip the sign and then add them together. But if you remember cathode minus anode, then you don't have to do all that flipping. Okay? These were both 2 electrons, so I didn't need to multiply anything together. I wouldn't have multiplied these values anyway, even if I would have had extra electrons. But it's still good to start noticing that your N equals 2 electrons here. Just start noticing that information because that's going to come into play in another day or two. All right. Now this is already built, but I want to talk to you about how we would go about doing that. Okay. So when we're building these batteries, I always put my anode on this side. That's just the way I do. And then I've got my electrons going to this side. Okay. So I've got my anode over here. I've got my cathode over here. I'm going to have in here, I'm going to have some sort of solution that the zinc is going to be going into. And typically this is going to be like zinc nitrate, zinc something. Okay. It could be zinc chloride, anything. But you're going to have these zinc 2+ ions floating around in here. Okay. I'm also going to have zinc here. A piece of zinc metal. Okay. This is going to be pure zinc ions in here. And maybe I should do that in that color so you can see the difference. So this is going to be zinc. This is zinc, complete zinc. Okay, no charge. Got it? All right. I am then going to have a wire set up, and that wire is going to lead to here. A lot of times it'll have a voltmeter, and that voltmeter is going to read 1.10 volts. How do I know? Because we just did that calculation. Okay. That is then going to lead over to here. And what is that going to be attached to? A piece of metal. And that piece of metal in this case is going to be copper. Okay. So now I've got copper here. It's hanging out. Copper, copper. Okay. And then that copper is going to be in a vat that has copper 2 ions in it. Okay? Everybody cool with that? I am then going to have a salt bridge. Okay, I'm going to need something that as this zinc is coming in here and adding more positive charge in, it's going to be balancing that charge out. And as this copper 2 is depositing on here, is going to be balancing that charge out. So that's my salt bridge. So I'm going to have something here called a salt bridge that's set up. And typically this will have 2 neutral salt ions in it. So something like potassium, because that would be part of KOH. If it went in with water, it would still be a neutral salt. It wouldn't bind up with something else and change the pH. And I'm going to have something like a nitrate in here. Okay. Oops, that's a minus. Shoot, let me try this again. I don't want it in that color anyway because I've already used that color. And it should be a minus. That probably you can't see purple. Good. Okay. So NO3. 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 And then I've got to add some more potassium in here too. All right. So we've got this all set up now. All right. We're going to start moving things around. So pay attention to how this works. Austin, you with me still?
Yep.
Okay. Because this is kind of the newer part that we didn't really get to last week. All right. And this is where somewhere I had a smartboard simulation, but I can't figure out where it is. All right. So what's going to happen is, and if we look back at that equation that we drew out, one of these zinc molecules here is going to come off, okay? It's going to cleave off 2 electrons. It's going to give off 2 electrons, okay? When that gives off 2 electrons, we lose that piece of zinc. It's going to go over here and become a zinc 2+. Okay, it's going to go into solution. It's becoming an ion because these 2 electrons have come off. Does that make sense? Those electrons are going to move this direction, and we know that because it moves from the anode to the cathode. We know that this is the anode because it was a negative 0.76. We know that this is the cathode because it was a positive 0.34. Thank you. Volts. So this is the more positive of the 2. So we know our electrons are going this direction. So those electrons are going to come across here. They're going to hit this copper. They're going to travel down this copper, and it's going to grab a hold of one of these and deposit that onto here. So we're going to pull out 2 of these. We're going to add that guy in with these 2 electrons that have come across, and we're adding more copper here. Now, what's happened here now is that I've lost 2 positives off of here. I lost one of these. He went into here, right? So I've got to bring down 2 of these potassiums, which I don't have it in the right color, but just deal with it. I've got to bring those 2 potassiums down to balance that charge out into here. I also have added in a +2 here. So I need to bring in 2 nitrates to balance out that. That balances out that charge that just got added in. That makes sense? Kind of neutralizes it essentially. And these two guys will go away. Okay? Now, we keep doing that transfer until we run out of something. We might run out of stuff in our salt bridge, or we might run out of this anode. When that happens, what happens to your battery? What do we say happened to your battery?
Dead.
It's dead. Yeah, because you've run out of this. Because eventually this is going to start going away and withering away and becoming less and less until you don't have that anymore. This is going to become bigger and bigger. That's why they call this a fat cat. Because this is going to get bigger. Your cathode gets bigger as these electrons come over and this moves in. Does that make sense? You're going to hate me for this. It's going to get in your head, and that's good. I want it to. All right, here we go. Present a tab, and I want to present this one. Let me know if you can hear this, Austin, or if you can't, I guess. And the rest of you, listen up. This is great music. It's no Beyonce or whatever y'all listen to.
Is this electrochemistry? You take two half cells and connect them up so well with a load to power in between. You need to have electrodes, you see, full of that metallicity. Let electrons flow across the salt bridge we go, allowing us to make electricity. We start at the anode, electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where we start at.
So that will get in your head if you listen to, like, they have this going for like 3 more minutes. But the idea is that you're starting here, okay? And when the electrons are lost, you're going to take a little bit of that metal off, okay? Those electrons then flow across there.
And go through the wire and through the load on fire.
Okay, so they're going to go through here. They're going to go through the load, and that's whatever you're powering, be it your calculator, your phone, or whatever. I don't know why they say on fire. That doesn't make sense to me because the thing's not on fire. But the electrons they're going to come down this wire, and it's going to go to your cathode, whatever that is.
Enter the cathode and reduce the cations.
Okay, and see when they reduced that, do you see how it got that little bulge out the side there? These electrons are going to, and it adds to it. And so this thing actually starts to build up and you get more. And then you have to balance the fact that those two, now not only the anions go through here, but you also get cations that are coming out here to balance this charge. So you kind of missed that on the video, if you ask me. And then the anions come over here, and then the whole thing repeats. And he just keeps repeating this thing over and over and over again until you're just ready to scream. Which I won't put you through unless you don't watch my next video. That is your penance. All right. Okay, so that takes care of that diagram. Let's go over here and drag this back over. So we were looking at, went through that with you, and then we're considering a galvanic cell based on this reaction. So let me copy this, new, and I can increase this guy, and then I can draw in here. Okay. So they want us to, so we need to figure out what is being reduced and what is being oxidized here. So figure that out. Go. I get something to drink. Breathe again. So what happened to this guy? Did he lose or gain electrons? Okay, so he's oxidized. So that means that our magnesium oh, this, wait, I had this backwards. Let's try that again. Ay, ay, ay. What are you guys going to do with me? All right, so he decreased charge, so that means that he's reduced. This guy increased his charge. That means that he's lost electrons. Okay? So I'm going to look up my potentials here for this after I balance my, they want us to have a balanced, and then calculate the E cell. So I'd go AL 3, well, you guys do this. You figure it out. And I want to know what N equals too. Oops, I gave you that. Forget it. Ah, cheating. All right, get this thing balanced. Go. Grumpy. Should know how to do that from Unit 4. I just showed you at the beginning.
I mean, I understood it.
Okay, so do you see here I've got three positives here? Do you see the 3 right here?
Yeah.
Okay. If I add in 3 electrons, that's going to give me this aluminum, correct?
Yeah.
Okay. If I take my magnesium and I'm going to go down to Mg2 plus, how many electrons will I have lost in that process? Good. What's the least common multiple between 2 and 3? 6. So I need to multiply this by what to get this to 6? 2. And I need to multiply this by what to get this to 6? Okay. I got to go down here because I ran out of room. So this is going to be 2Al 3. Oh, I guess I could probably just erase and do that. 2, 2, 2. And this guy is going to end up, no, that wouldn't be 2, that would be 6. This guy will be then 3, 3, and 6. Do you remember how to do these now? We did these back in Unit 4. All right, then if we do a balanced equation here, we're going to get rid of the stuff that is the same, you know, on from each side. So the 6 electrons will go away, and then we just bring the rest of this together. Remember how to do that? Do you remember doing this?
No. Well, I mean, okay, I remember doing it. I just don't remember how.
Does this make sense now? Do you know how to do it now?
Not yet.
Okay. So this will come together. This 3Mg comes together. My 2Al plus 3Mg2 plus. And that is my balanced equation, N equals 6. And I got that from right here. Yes, sir.
So really, all you have to do is, so you find the least common multiple and then associate it with you just throw them in as the coefficients to the normal equation.
Uh-huh.
Right. So the only reason you do like that is to find the n.
Mm-hmm. Which we're going to need, but not today. All right. So I've got that taken care of. If I go back and just look at these equations and find my potentials for these guys, okay, I'm going to look back on that reduction potential chart, and I'm going to find my aluminum that's lost 3 electrons or gained 3 electrons, and my magnesium with 2. Okay, so we're going to go back to this chart here. We're going to find our aluminum on this chart. I think this one might be easier to read. Aluminum's here, so that's a negative 1.66. So aluminum is, Al is a negative 1.66, and the magnesium,
Who's right above it?
oh. No, that's manganese, honey.
There's almost 2 below it. The AL.
Okay, there it is. So that, and it's 2. And make sure that you check for 2, because these things that have multiple oxidation, you know, you got to check. So negative 2.37. Now, this number is more negative. This one, aluminum, is more positive. So this one should have been reduced, and it was. And this one was oxidized. So we're verifying that. Remember, it's cathode minus anode. So our cathode would be our reduction. That's our aluminum. That's a negative 1.66 minus a negative 2.37. And I get 0.71, and I'm hoping that's what she got. Good, I did good, okay. So that equals a 0.71 volts, and that would be my reduction potential for this guy. See how I got that? Cathode minus anode, cathode minus anode, cathode minus anode. All right. So that takes care of that one. That takes care of A. Let's look at B here. All right, this is based on the reaction. They want to give a balanced E-cell reaction here, and then calculate E-cell for this. So check out and see your see if you can see what's reduced and oxidized on that one. Got that song in my head. It's like a worm. You lost? Need more time? Austin, how you doing? You need help on this? This making sense?
I put my answer in chat. I didn't know if you wanted me blurting it out.
That's what went bleep.
Yes, it was.
Okay. E L oh, reduced and okay, I got it. Okay.
How do we write how do we put the balance of the reduction of the...
Okay, so your manganese here goes from Mn04 minus, right? It's going to go to Mn2 plus. So here, if this is a minus 2, right? Minus 2 times 4 is a minus 8, so this is going to be a plus 7, right? There's a plus 7.
So are we just adding 5?
Yep, 5 electrons for this one. Yep. So let's see, that would have been plus 5 electrons, gives us this thing. And then our ClO3 minus will give off 2 electrons to get to ClO4 minus. So yes, the manganese is reduced in the chloride, chlorite, hypochlorite, whatever it is getting oxidized. Good job. I heard something go bleep and I didn't know what it was. That's what it was. All right, so then I've got to find the least common multiple between these, which would be what? 10. So I've got to multiply all of these things by 5. And all of these things, or all of these things by 2 and, no. Yeah, top by 2, bottom by 5. You're right. When you're right, you're right. This is a 5, 10, and 5. So N equals what here? Okay, and you need to know that for later, but I'm getting you in practice now. You're going to be like, oh, thank you, Lippy, for making us call ourselves attention to that, because we're going to need that. And then we are going to combine this guy together, and that would be 2MnO4 minus plus 5 ClO3 minus yields 2Mn2 plus 5 ClO4 minus. All right, we look these up on our chart, and this is a 1.51 volts, and this one is 1.9 or 19 volts. And if we look at this, we can see that this is more positive than this. So the more positive one is going to get reduced. This one will get oxidized. We can also look at the equation. That's what you guys did up here to figure this out in the beginning. There's a couple of different ways you can tell. All right. So
which chart do we look at?
this would be that second chart that was on there. So it'll be over here, isn't it? Right here. The first one's right here, I believe. 1.51 is right here. See that? Find the thing that says 1.51 over here.
Yeah, so I'm just confused with that water in there. That just makes sense.
Yeah. But you can find the MnO4 right here, yes? And it goes to here. And if you look at that original equation, that was there. The H's and the waters. I just pulled the stuff out of it. And then the other one was, maybe that one wasn't given on here. Maybe I had to get that from the video. Anyway, they're only going to give you ones that you're going to have on the charts. All right. Yeah. Well, it's here. I've given it to you. You're okay. So we're going to go cathode minus anode. Okay. So our cathode is the one that's getting reduced. So that's 1.51 minus a negative. Wait a minute. Did I do that right? Oh, it's a positive. This one's a negative and this is a positive, right? No, this one, they're both positives. They're both positives. There. So minus a positive 1 point. Thank you. That's what I did wrong. And then if we subtract that out, we get a 0.32 volts. These reactions will run if you have them set up, if you end up with a positive voltage here. If you end up with a negative voltage, then it's not going to run. Okay. All right. So I want you to, for homework tonight, I want you to try to set up your sample problem here for the next page. So after exercise 1, I want you to try to figure out sample problem. You will have an inert, you'll have platinum for your cathode ion because you're going between Fe2 and 3. So just see if you can do that. That'll be what we start with tomorrow, and then keep working on your final exam and your problems, okay? Austin, you good, honey, before I quit?
Yep, I'm good. See you, Lippy.
Okay, I'll see you tomorrow, honey.
Yep.
You didn't warn me that this is almost